Hello everyone. I wanted to take a few minutes to give you a walkthrough of the confidence interval section so you know what kind of stuff we're dealing with. So the big picture is that when you report an estimate, in a statistical analysis, you will want to estimate some number, like the mean of a population. And it's not enough just to say one number. Say, oh, I think the mean is here. The right thing to do is to say, well, I think it's here, but it could be anywhere between here and here. So the standard way to do this is called a confidence interval. And the confidence interval comes with a parameter, the level of confidence. For example, a 90% confidence interval says roughly I'm 90% sure that the parameter is somewhere between here and here. Okay? So the main tool, you already know all the math. So in the previous section on estimators, we learned how to generate sampling distributions for any estimator. Okay, so remember the sampling distribution tells you the variability of the estimates you can obtain. So here's an example for the kombucha population. We know it's roughly 1,000, so this is the mean of the population is 1,000, but the variability of the samples we can expect is anywhere between 995 and 1,005. Okay, so the sampling distribution contains the complete information of the uncertainty of the estimates, but that's too much information. Basically, you can't report a graph in a paper. I mean, you can, but it would, the convention is not to show the graph, but to summarize. So here's what we're going to do. If I find the right shortcut, we're going to take a region in the parameter space that contains roughly 95% of the probability mass. And when you want to report an estimate, you're going to report from 995 to 105. Okay, so these are just two numbers that summarize the whole distribution and saying, well, like it could be below that, but it's very small probability. And it could be higher than that, it's very small probability. So this is an example of why you need confidence interval. It's just a summary of the variability you can expect in a sampling distribution. So nothing new mathematically speaking, but it's super important. You see a bunch of formulas for obtaining these confidence intervals. Okay, so I'm going to close that. The confidence interval is a general thing, but we're going to talk about specifically confidence intervals for the mean. So if you're interested in, you have a sample mean computed and you want to know the population mean or the variance. So if you have a variance and you want to know what's the population variance, and the third one we looked at in the previous section is the difference between means. So you have two populations, computed the means. What is the real difference between the population means? Okay. Here is the code for the estimators. Remember, these are the estimators we learned about in the previous section. So the mean, the sample mean is an estimate for the population mean, sample variance, estimate for the population variance. So all of these, we'll call them point estimates. So just, it's a single number that tells you the best guess about the population mean. And in this section, we're going to learn how to build a confidence interval. So instead of just reporting a number, we're going to report a whole range of numbers. That's what an interval means, right? It's numbers between here and here. Okay, I'll let you read the definitions. Remember, this is the sampling distribution, the main building block. We're importing from in the last section we learned bootstrap procedures for obtaining sampling distribution, and analytical approximation. So in this section, we're going to continue this parallel structure, and we show both methods for computing confidence intervals. Okay, so here is the definition. Okay, there's really two new concepts here. So the first is this idea of coverage probability. Okay, it's really just a parameter. Do we take the bulk of the distribution a 90% bulk or 10%? Like, like the parameter, how much confidence, how wide do we take this interval? So a 90% confidence interval is constructed by cutting off, right? So we want 90% to be captured, to be in the middle. This means we cut off 5% from the bottom, 5% from the top. Okay, all the examples I'll give are with 90% confidence intervals, but in general, gamma is a parameter. Usually people choose 99, 90, sometimes 80%. Okay, and the only new concept is confidence interval. Okay, so confidence interval is a range of numbers, the lower bound and the upper bound, that contain the parameter theta gamma percent of the time. Okay, now there's this weird technical detail, but you know me, I'm not gonna spare you the details. There are two, we call confidence interval, but there are actually two things. One is confidence interval computed from a random sample. So you can think of this as a procedure in general. Given a sample, what should you do? I'm going to compute this step. So this notion corresponds to the long-term probabilities. So like if you were to repeat this procedure with a new sample at a random sample, so that's what a random confidence interval describes. I want it to be clear that it's different from a particular confidence interval, which is just two numbers. So these are two random variables. The upper and the lower limit vary depending on the choice of x. And this is one particular instance when we have one sample and we computed the bounds, upper and lower bounds. The reason why I make this distinction is that the probability claims, we're going to make some statement like this confidence interval works 90% of the time. We actually making it, so here's the specific probability statement, that the probability, the confidence interval will, the parameter, the true parameter will be inside the confidence interval is 90%. So note we're using the capital letter here. So I'm making a statement about, when you use this procedure, what's the probability of success? The lowercase one is for one particular sample, and there we cannot make any guarantees. I mean, it could be correct, it could be inside, or it could be outside. But we have no guarantee. We know just that the procedure we use will work 90% of the time. So here's a picture of that. Here's a little bit wider picture. Will hopefully make things clear. Okay, so we have a population with mean 100 and standard deviation 10, and from that population we have drawn 50 different samples. Okay, from each of these samples we computed a confidence interval, which you can see with this interval notation from here to here. And the 90%, like the way we computed the procedure, the goal is that 90% of these confidence intervals we've computed from the individual sample will contain the true parameter, so the mean 100. And let's see this. So the reason why these are different, first of all, because each sample from the population will have different mean, right? We saw that sample could be anywhere between, there's an inherent variability in the mean, and it's also the way we construct this confidence interval depends on the standard deviation of the sample. So because of the natural variability of the samples we obtain, we're going to have different confidence intervals in each of these, for each of these samples. And on individual, and that's what the procedure we used, you see, it captures the mean. To capture means to contain. It contains the mean most of the time. All the black ones are good, but there are a few red ones that didn't capture the mean. So this sample, the mean happened to be really small, and the standard deviation is normal. But you see, you know, the estimate we computed from this sample, the confidence interval, it's wrong. Same for this one, same for this one, same for this one. So that's what 90% confidence means, is that on average, when we repeat this procedure for 100 intervals, 90 of them will contain the true parameter, 100. In this case, so 90% means roughly 45 out of 50 of these intervals will be correct. In our case, we got 4 wrong, so we're roughly, you know, as promised, it's working. Okay, how do we build these confidence intervals? Okay, so roughly speaking, right, we saw the high-level pictures that we want to cut off. We have the sampling distribution. We want to cut off for 90% confidence. We're going to cut off the bottom 5% and the top 5% to remain the 90% of the probability will be between these two bounds. Okay. Mathematically, this is done using the inverse cumulative distribution. Okay, so if you remember it, so this is the cumulative distribution, and with the inverse, it means it's the opposite. So given a particular quantile, it tells you the position, where the cutoff, where to, you know. So this entire section can be summarized by this equation. Like if you know the sampling distribution, to build a confidence interval, you need to cut off the bottom alpha over 2 and the top alpha over 2. So not super exciting, but that's how it's done. We'll actually show 2 ways, right? Remember, we found a way to compute confidence intervals, sampling distributions using bootstrap or using analytical formulas. So we'll similarly do the same thing with confidence intervals. So here is a bootstrap. Remember the function? It generates bootstrap samples from a particular sample. So this gives you a way to generate so bootstrap samples for the mean. This list here contains the possible means, the variability of the mean for this sample. Okay, and if you want to have a 90% confidence interval, so this is a long list. We just cut off the bottom 5% and the top 5%. So this is how, given a list of observations, the percentile method says, you know, sort them and find me the lowest, well, this is reversed, the lowest 5% and the highest 9%. And that's how you obtain a confidence interval, by cutting off the two tails. Equivalently, the quantile method works exactly the same way, but you give quantiles, so the numbers between 0 and 1. Here is percentages, but it does exactly the same thing. Okay, so we'll use that a lot. So bootstrap confidence intervals, really easy way to do this. You'll see with the examples below. The other way is using analytical approximations. So again, this cutting off the bottom alpha over 2 and the top alpha over 2. When you have a probability model for the sampling distribution, right, you have an equation. I don't put the equation here, but the standard normal is e to the minus x squared, You can do cut off the bottom, so this is the location of the alpha over 2 quantile, and this is the location of the lower alpha over 2 quantile, and this is the upper alpha over 2 quantile. So when you have that, the equivalent of the inverse cumulative distribution function in Python is called the PPF, point percentile function. Same thing. That's the name of the function. I'm not, they could have said capital F inverse. And so this is how you obtain this number, the upper 95%. And I'm showing these 6 examples just to show the 5 different ways. So you can obtain the standard normal, a computer model for it, by specifically saying, okay, this is the location 0 and scale 1. That's what standard normal means. Or you can skip the location, you can say 0, 1. Or you can just say norm. The default parameters are mean 0 and standard deviation 1. Even better, you can just call norm the class. It has a class method that does this for you. Yada yada. You can look at the example. It's just, this is the shortest version. So in here, there's implicit that this is a 0, 1 norm. If you don't write it, Python will assume it's the standard norm. Okay, so finally, so here's the example. You compute the bottom alpha over 2 quantile, the top alpha over 2 quantile, and you just, those are the limits of your confidence interval. So it's very straightforward. If you know how to use probability distributions, it's the same. And for the t distribution, it works exactly the same way. So we'll see those come up in other examples. So note, however, the t distribution takes a keyword parameter, the degrees of freedom. All right, so let's continue in the next video, confidence interval for the population mean. Oh yeah, here's the visual for cutting off the bottom alpha over 2 and top alpha over 2. Yada yada yada, for the population mean. All right, continuing.